We are recording and we are now in chapter 10. We're going to talk about vector functions. And in the intro to vector functions, it mentions that the functions that we have been using so far have been real valued functions. In other words, you have a function, for instance, of two variables. You put in values for the two variables, you get out a function value. Now we're going to study functions whose values are vectors because such functions are needed to describe curves and surfaces in space. Okay, so movement through space, three-dimensional space, we use vector functions. Now they mentioned that they actually are going to use vector functions to derive Kepler's laws of planetary motion. We won't get into that, that's a physics application, but nevertheless, it's there in the textbook if you're interested. So, all right, let's go ahead and proceed through here. Hold on, do I want this? That's not what I want yet. Hold on. I want to go down. Here we are. Okay, so in general, a function is a rule, and you know this, that assigns to each element in the domain an element in the range. A vector valued function or vector function is a function whose domain is a set of real numbers and whose range is a set of vectors. Okay, so to make this a little more understandable, let me see here, I just want to, hold on, I got a lot of stuff. Here we go, this is what I want. So this is how we view a vector function. The vector function r, and notice r is in bold letters. That means it's a vector. But this vector is a function of a parameter t. Well, a vector in three-dimensional space has to have three components: an x component, a y component, and a z component. Well, these components we're going to be represented by f of t, g of t, and h of t. And so we can write the vector in the component notation or the IJK notation. Now, let's look at an example of a vector function. Okay, so in example 1 here, we talk about the domain of a vector function. A vector function, like any function, has a domain. So let's say that your vector function has components t cubed, and then the natural log of 3 minus t, and then the square root of t. They're your component functions, okay? F of t, g of t, and h of t. Well, what's the domain? What's the domain? Okay, in other words, the vector function r is a function of time, of t. But t can't be all real values, because we have some functions here, we have some components, namely, you know, this log function here, and this square root function. I mean, those functions are not defined for all values of t. Well, when is the log function defined? It's defined for numbers that are greater than 0. So as it shows in the highlighted part there below, 3 minus t has to be greater than 0. But then the square root function, h of t, square root of t, t has to be greater than or equal to 0. Well, if 3 minus t is greater than 0 and t is greater than or equal to 0, the domain is going to be the closed interval 0 to 3, and where 3 is open. Let me see if I can help you feel comfortable with that. Let me go in here. So we agree that for this example 1, the vector function would be defined if 3 minus t is greater than 0 and t is greater than or equal to 0. Both of those have to be true. Well, if 3 minus t is greater than 0, then 3 is greater than t, or t is less than 3. So we get t is less than 3, and t is greater than or equal to 0. This is a compound inequality. And if we were to draw that, on a number line here, here's 0, 1, 2, 3, t-axis here, -1. Well, all right, t less than 3 would be here. But then t is greater than or equal to 0. So it stops there. So this is why this is your domain for t. Well, the domain for the vector r is this interval. Are there any questions on that? Okay. Okay. Well, let's go back to the book then. Okay, and so we now understand where that answer comes from. One. Okay, let's continue on. So, of course, a vector function can have a limit as t approaches a number, so long as the components, the 3 components of the vector function, also have limits. I mean, it makes sense. It makes sense. I mean, if we, for instance, looking at this second example, okay, they want you to find the limit of this vector function as t approaches 0, and the vector function has components 1 plus t cubed, t times e to the negative t power, and then sine of t over t. And if you want to take the limit as t approaches 0 of this vector function, well, they show you here what that limit is. It equals the vector I plus k. Okay, so clearly, as t approaches 0, well, I'll tell you what. Why don't we take a look at these limits in the whiteboard? So we have 3 separate limits here to compute. So let's just peek at them here. One moment. So here was one of the limits. How many remember doing this kind of stuff maybe back in Calculus 1, finding limits? Sure, Simon remembers that. Norina remembers that. Brian and Yeva. Mary. Well, the first function, 1 plus t cubed, yep, equals 1. That because this is a continuous function, right? 1 plus t cubed, that's a polynomial. So you can just substitute in the 0 for t. Now the second limit is, hold on, it's this limit, which we can write as the limit as t approaches 0 of t over e to the t, right? Well, so that's not an indeterminate form. The numerator goes to 0, the denominator goes to e to the 0. That's, hold on here. Now wait, hold on. Let me examine this a little more here. One moment. This should be, yeah, that's right. 0 over 1, that's 0. So no problem there. Those limits are easy. Okay, now let's look at this last limit. The limit as t approaches 0 of the sine of t all divided by t. So as t goes to 0, right, the sine of t approaches the sine of 0, which is 0, and t also approaches 0. So this limit we have the numerator approaching 0 and the denominator approaching 0. How do we, so that's called an indeterminate form. For such an indeterminate form, do you remember a special theorem that can be used to find the limit of that indeterminate form?
Is it L'Hopital's?
That's right, Devasina. That's right, Norina. Excellent. L'Hopital's rule. That's right. So we're going to use L'Hopital's on this. Well, the derivative of the sine is the cosine, and the derivative of t is 1. So now we can just compute this limit as the cosine of 0, and that equals 1. Okay, so are there any questions on that? Everybody must have seen L'Hopital's rule. That's standard to cover in calculus. So okay, so now we know the limit as t approaches 0 of r of t, okay, which is the, so I'm just example 2, I'm just basically putting it here. It's the limit as t approaches 0 of, right, 1, the components are 1 plus t cubed, t times e to the negative t, and then sine of t over t. And that's just going to equal then, well, it's going to equal the vector 1, you know, because 1, 0, and 1. Okay? Which also happens to be equal to I plus j. And that's, sorry, I plus k. I plus k. Okay. Are there any questions on that? Well, what happens is when you take the limit, let me show you here in the whiteboard here. Hold on, wait. One moment. Yeah, so we're taking the limit as t approaches 0 of this vector function r of t. And that limit equals a constant vector, I plus k. We had to use L'Hopital's rule to get the third limit, and so hold on here. But they didn't show that. They didn't show that here in the example. But now you know how they're getting those. So L'Hopital's rule is something you'll from time to time need to use. Are there any questions so far? Okay, let's keep going. Let's keep going. So you learned in Calculus 1 about continuity. Okay, and there's an analogous definition for vector functions. If the limit of your vector function as t approaches a equals some vector r evaluated at time equals a, it's continuous there. And we can, I mean, these vector functions, it might help to have a little picture here. This is a picture of a vector function. So you see, you have the vector r that's drawn from the origin. R of t is drawn, that's called a position vector. Often we call that a position vector. It's drawn from the origin. And as t changes, the vector r, the components of the vector r change. And so you trace out many different points in space, and it traces out this space curve. Okay, it traces out this space curve. So the space curve C is traced out by the tip of the moving position vector r. So remember, as t changes values, the position vector r changes too. Well, think of that position vector r changing through space, and think of the tip, the points on the tip changing, and it's going to trace out a space curve. That's what we're doing, and of course, in this situation, okay, so here now they're getting into the basically what I'm saying. These equations, f of t, g of t, and z of t, are your parametric equations of your space curve, and t is your parameter. So, as it aptly says here, we can think of this space curve C as being traced out by a moving particle whose position at time t is given by those coordinates, f of t, g of t, and h of t. And that's exactly what they have drawn here in figure 1. Are there any questions on that? Okay, well let's move on here. So in example 3, they want you to describe the curve defined by this vector function. So look at the components of those of this vector function. Look at its components. The first component is 1 plus t. So the x component is 1 plus t. The y component is 2 plus 5t. The z component is negative 1 plus 6t. What do these components have to be coming from? They are parametric equations. That's right, Alexander. Parametric equations of a, that's right, Yeva, a line in three-dimensional space. It could, so think of it like this. Think of it like this. Okay, let's think of it like this. Let me write the, add a little detail here. Hold that thought, Aura. So, example 3 from section 10.1, R of t equals 1 plus t, y of t equals 2 plus 5t, and the third component is negative 1 plus 6t. If you were to write x equals 1 plus t and y equals 2 plus 5t and z equals negative 1 plus 6t, okay, this here, these are parametric equations for a line passing through some point and parallel to some vector v with components. So you just took the first exam, right? The first version, at least. What's this line passing through? What point is this line here? Okay, given by these parametric equations. Good. Good, Lexi. Good, Yeva. 1. Good, Alberto. 1, 2, negative 1. Okay, line passes through that point. Now to lock in the line uniquely, we need to know what vector it's parallel to. Good, Norina. Good, Yeva. 1, 5, and 6. Those are the coefficients of the t's. So this vector function here, and notice t can go from negative infinity to positive infinity. There's no limitation on the domain of this vector function. That's a line through space. That's all it is. Okay. Are there any questions on that before we move on here? Okay, that's example 3. Let's keep going. Now they make another comment that, I mean, we're looking at curves in three-dimensional space, but plane curves are curves in two-dimensional space. They can be represented also by vector notation. Okay, so if you had parametric equations x equals t squared minus 2t and y equals t plus 1, you would represent the vector equation that way. You've actually done this before. You just probably didn't realize it. Let me do something here with you. I always like to try to relate new material to the past of what you learned, because I think it provides some framework for you. But I mean, here's a very famous example. Well, okay, let's say you have x equals cosine of t and y equals sine of t. Those two parametric equations, and t goes from 2 pi, say, to 0. What would this trace out in the xy plane? I mean, what are those parametric equations going to trace out? That's right, Lexi. It's going to trace out a circle of radius 1. And so I don't know if maybe in pre-calculus you remember doing this. In pre-calculus, you would be presented with some parametric equations. And based on the parametric equations, you can graph the curve. And, you know, for how many remember doing this in pre-calculus? Yeah, Alexander recalls that. I've taught pre-calculus. I know it's covered. Christopher recalls that. Good. Well, you know, we can analogously write this vector equation. R of t has components cosine of t and sine of t, where t goes from 2 pi, or it goes from 0 to 2 pi. And you'll have a position vector, okay, that we'll label it. I mean, what it is, R of t, right? And components are cosine of t, sine of t. Okay, so again, in multivariable calculus, you trace out the space curve. The space curve is traced out, whether it's 2 dimensions or 3 dimensions. It's traced out by this position vector as it changes with time. Okay. Obviously, for this one, this is a simple one. You know, here, I mean, you're starting at t equals 0 there, and then you wind up at t equals 2 pi. You arrive back there. So, all right, just kind of some simple ideas. All right, let's take a look at some other things here. Let's keep going here. Helix. Example 4, sketch a helix. You all know what a slinky is like, right? A slinky. And you know your DNA is in the shape of a helix, right? So a helix is a very important idea. How, though, would we describe a helix? You know, how would we describe that? Well, you need 3 components because a helix is in 3-dimensional space. R of t could equal cosine of t. Well, R of t could have components cosine of t, sine of t, and t. And if you use that, I have to have it a little bit This is what gets traced out. I wish I could kind of have it. Let's see here if I can maybe. One moment. One moment, class. I want to try something here. Nope, that won't work. Well, nope, that won't work. Oh, okay, never mind. Let me go back to the ebook. Okay, so you can, the helix is here. It's drawn in figure 2, and it starts at 100. Okay, for for our purposes. So you might want to just jot the helix components down. Okay, or actually I'll try to have them visible here along with the picture. There we go. Hold on, let me just move that up a little bit. Okay, yeah, that works. That's perfect, actually. So what's going on here? What's going on? So the space curve for this helix with the components x equals cosine of t, y equals sine of t, and z equals t. The space curve is going up with t. So as t increases, the space curve, the arrow goes in the direction of t when t increases. So the space curve is going up. What controls the going up part of the space curve? What controls it going up? The x component, the y component, or the z component? Good, the z component. So z equals t. That's right, z equals t. And so as t increases, this helix, the space curve has to go up. Now, that's like the vertical behavior of the helix. Now we can talk about the horizontal behavior. What's happening horizontally? Not exactly horizontally, but the x component's the cosine of t, the y component's the sine of t. If you didn't have the z equals t there, if you didn't have that third component there, x equals cosine of t, y equals sine of t, in this example 4, would trace what out again? What would those two components trace out? Good, a circle of radius 1. That's right, Alexander. That's right, Mary. So think of us, think of moving around and around the circle. That's right, Brand. You're going around and around in a circle, but now you got the z component. So as you move around in a circle, you're also being lifted up as you're moving around the circle, kind of like an airplane going in loops, but going upward. You see that? You see, does that make sense? And notice also here that, well, it's there and highlighted. If you take x squared plus y squared and square those components, you get 1. So the curve has to lie on the circular cylinder. X squared plus y squared equals 1. Every point on that curve, on that space curve in red in figure 2, has an x, y, and z component. But the x and y components, the coordinates, all have, those coordinates themselves have to lie on a circle of radius 1. So that's why they say well, Yeah, that's why. I mean, hopefully I don't need to get too complicated here, but this is called a helix. And I think probably everybody knows this, but they comment here that the corkscrew shape of a helix, maybe I'll highlight this, such a beautiful thing. Corkscrew shape of the helix is familiar from its occurrence in coiled springs. It also occurs in the model of DNA. Okay, so the structure of DNA, that's what you're made of, and I guess everything, right? Uh, it's two linked parallel helices. Okay, are there any questions on this so far? All right, let's try a few more examples to go. Okay. In example 5, this example, they want you to find a vector equation and parametric equations for the line segment that joins one point to another point. Well, you know how to find the parametric equations for a line set. You know how to find parametric equations for a line. Well, finding parametric equations for a line segment works the same. It's just you have to restrict your value of t because it's a line segment. Okay, it's a line segment. So, I mean, here, this is what we are trying to find a vector function for. And notice the line segment starts at the point P and it ends at the point Q. Okay. So I don't know if you remember this equation, but to get the parametric equations for a line segment, how many recall this from section 9.5? This highlighted formula. Well, it's very useful. I mean, it's very useful. We talked about it briefly, but any line segment, you can find the vector function by taking a linear combination of the starting point and the ending point. 1 minus t times the starting point, r sub 0, plus t times the ending point, r sub 1. And t is between 0 and 1 automatically. You don't have to think about what the range is on t, like what the limits are on t. And so in this problem, quite beautiful really, they just apply that formula. They just apply this highlighted formula, and you'll get your answer. What's nice about the formula is there's no like you don't have to figure out what the limits are on t. So it's really quite nice. Okay, I'd like to do one more with you before we take a little break, and I'll have you do some work here, a little bit of classwork. Example 6. Okay, now if you have two surfaces and the surfaces intersect, you're going to get a space curve. So in example 6, they want you to find the intersection of, well, they have a vector function. Well, Find the vector function that represents the curve of intersection of a vertical cylinder and the plane y plus z equals 2. So they have a picture here. They have a picture. And we'll get into MATLAB soon here. But here's a picture of the situation. Cylinder, vertical cylinder with radius 1, intersects the plane. And what would the intersection look like? Would it be a circle? Good, Mary. It wouldn't be a circle. It would be an oval, like an ellipse. You're absolutely right. Absolutely right. That's what it would have to be. And it makes sense based on the picture. So what we're looking to do is we're looking to find a vector function to describe this space curve. Now the space curve, are there any questions on that so far? Yes, Mary.
Is it kind of similar how if you have two lines or two curves on a 2D plane, how the intersection, that point, is that the same thing, but instead of it being a one point, it's a line, right?
Well, two planes, if they intersect, if they're not the same plane, they're going to intersect in a line, right? And that line is itself a space curve. That's true. So we're doing the same. We're doing a similar exercise here. It's just we have a plane intersecting a cylinder, and the space curve, that's the intersection of those two surfaces, happens to be that ellipse or oval. But Mary, I'm not sure. Did I answer your question, or maybe not quite?
Sorry, I didn't mean to do that. Yeah, you answered it. Thank you.
All right, you're welcome. You're welcome. So, okay. So you notice they have some points here. They have some points on this oval here. And I'd like to try to see, let me just see if I can get kind of both of them to, one moment. Obviously I can't have it too small, right? You notice on that figure 6, they have some coordinates. They have some coordinates on the space curve. So those coordinates, like if you look at the coordinate -1, 0, 2, that point, is that point -1, 0, 2? I want to say this the right way. Is it on the plane? Is it on the cylinder? Or is it on both the plane and the cylinder? So figure 6, the point on the space curve, -1, 0, 2. Does that satisfy the equation? Well, let's do it step by step. Does it satisfy the equation of the plane? The equation of the plane is y plus z equals 2. Absolutely, it does. Good, Logan. Good, Brand. Yes. Does the point -1, 0, 2 also satisfy the equation x squared plus y squared equals 1? Does it also satisfy that? It does. That's right, Alexander, Logan, and Norita, and Brand. It does. And it has to, because it's on the intersection of both those surfaces. In fact, all of those points that they have there in the figure will satisfy both those equations. But now what we have to do, is we have to try to come up with a, with a parameterization. So if we go to the whiteboard here, so I'm trying to do, you know, some of these concepts using our whiteboard as well. But let me just go ahead and let's see here. I want to just, no, hold on. Okay. This is example 6, section 10.1. There's the oval, and I'll put a couple points on there that they had. -1, 0, 2, 0, -1, 3. We have X, Y, and Z. Okay. So, and we know, you know, for all of our little coordinates here, we do know that x squared plus y squared equals 1, and y plus z equals 2. Now we want to know, I mean, now think of this. Think of this. So think of a position vector, you know, coming out from the origin there, and we need to figure out what the parametric equations are, the 3 parametric equations for the components, parametric equations of C, right? That's what we, I'll label this here, C. What we're trying to find here are the parametric equations for the space curve. So, okay, well, I think we need to make use of these pieces of information here. We have 2 pieces of information. One piece of information is x squared plus y squared equals 1. So that means, you know, I mean, x is some function of t, and y is some function g of t, and we need that x squared plus y squared equals 1 always, for you know, always for any value of t. So what would work here? If you were to take that oval and slam down into the xy plane, if you were to take the space curve and project it down into the xy plane, what would you get? If you take this oval and if you were to shove it down into the XY plane, what would the trace be? What would the outline be of the oval, the XY plane?
Would it be a circle?
That's right. That's right, Mary. It would be a circle. It would, and what would be a circle of what radius?
1, I believe.
That's right. So that might help us. That might help us think about, you know, what the X and Y components are. What traces out a circle? What X component and Y component would trace out a circle of radius 1?
Cosine.
Good, Albert. Cosine of t. 1 cosine of t, radius 1. And what about the Y component?
Sine of t.
Yeah, that's right. 1 times the sine of t. Okay. So, yeah, that makes sense. That makes sense. And notice that x squared plus y squared always equals 1 by choosing these components for x and y. But now we got to find the z component. Well, they tell us that y plus z equals 2. That means z would equal 2 minus y. Z would equal 2 minus y. So what are we going to have then for the z component? I mean, it has to be 2 minus something, because z is 2 minus y. The z component would have to be 2 minus, what do you think? Well, what is y? Right, that's right. That's right, Logan, Mary, and Brand. Absolutely. It's going to be 2 minus the sine of t. Because, I mean, y, this is y, isn't it? This is y. And here's x here. But y is the cosine of t. So 2 minus, hold on, let me get that off. Two minus y is right here, which is 2 minus the sine of t. I mean, it's that easy. It's that easy. It really is. It really is. Now, what would the limits be on t to trace this oval out once around? What would the limits be, you think? That's right, Alberto, 0 to 2 pi. Now we can check this answer out, you know. I mean, we can check this answer out. We can try to confirm it. So like, for instance, the first point there, negative 1, 0, 2. Negative 1, 0, 2. What would, if this is our parameterization here, if this is our vector function, what t would this go with? What t would that go with? This point right here. Alexander says pi. That's right. Good, Alexander. because the cosine of pi, the sine of pi, and 2 minus the sine of pi equals -1, 0, and 2 minus 0, which is 2. So this coordinate here, I mean, what this is here, -1, 0, 2, that actually equals r evaluated at pi, that point. What about this point up here? What about this point right here? What t-value would go with that? Aura thinks 3 pi over 2. Let's check it out. Cosine of 3, that's 270 degrees, by the way. Sine of 3 pi over 2. And 2 minus the sine. It's getting a little cluttered here. Let me get this off here. One moment. We don't need this here. Two minus the sine of 3 pi over 2. Yeah, okay. Well, the cosine of 270 degrees is 0. The sine of 270 degrees is -1. And we got 2 minus -1, because the sine of 3 pi over 2 is -1. So that's going to equal 0, 1. Sorry, that's going to equal, let me do it right. Please let me know if you have any questions. I'm just trying to add some detail here to the example 6 in the textbook. Just trying to add a little detail to help give you a good feel. Zero, -1, and 3. Yep. And is this how many find this? Is this helpful? This adding some details sometimes to examples. Is this a helpful thing for you? Okay, wonderful. Yeva likes it. Logan, Aura, Norina, Sadana. Excellent, and many others too. Mary, Alberto, wonderful, wonderful. Well, Alberto, why are we plugging in 3 pi over 2? Well, so we took basically a good guess. You have to do a guess. So you know, t equals pi was for this point here, and it turns out that 3 pi over 2. You have the next t value for the later point on the curve has to be larger. Because you know, the t increases, and 270 degrees is the one that works. It would be the only one that works. And incidentally, I'll just mention this. Like the book also has a point down here. So let me just say this here, 0, 1, -3. That equals r of 3 pi over 2. That is 0, -1, 3. In the example in the book, they have a point 0, 1, 1 down here. That would equal r of what angle? What would 0, 1, 1 be? That would be the r of what angle? given these are your components. That's right, r of pi over 2. You see how this works, Alberto, you see how this works? Yeah, that's what you're doing. You're welcome. T changes values. As t changes values, the position vector moves, and the tip of the position vector traces out your space curve. All right. Are there any questions before I stop the recording here? Okay. I'll just to basically sort of complete the thought process here. I mean, well, we have done it, but just so you can see. You know, now, let me take this off here. So you see there's several ways you can express the answer. They're using vector notation. Well, they're using the IJK notation. That's the parameterization of your curve. There it is. But sometimes we just have the parametric equations as like component notation. So, all right, are there any questions? Okay, let me go ahead and stop the recording then.